Hey class, it's Dr. Franklin. I was wanting to touch base with you a little bit about where we're going in this class. Over the next 2 weeks, we're going to be covering Chapter 3. And in Chapter 3, we're going to be covering some algorithms about searching. In order to get to our searching algorithms, including our binary search trees, our balanced search trees, and our hash tables, we are going to be first of all, talking about the approach of using abstract data types, something called symbol tables, in order to construct the tools we need to be able to build the algorithms around those data types. So in this section, in 3.1, we are going to be talking about what symbol tables are, how they might be used, and a couple of elementary operations, as well as some more advanced operations, although we're not going to go so much through the details of how to construct those more advanced implementations, but we will talk about the change that is made to the API, that is the additional functions that become available whenever you introduce a more advanced implementation. So the two implementations that we're going to play with and toy with, or experiment with, I think is a better way to say that, in our homework are the unordered linked list implementation of a symbol table, and we're also going to be looking at the binary search implementation of the symbol table. So in particular, I want you to pay attention in this section to the order of growth calculations, or order of growth for those two particular implementations. Because search is so important to so many different computer applications, we find that the symbol tables, which is going to be this fundamental data type that we utilize to implement our different search algorithms, they're available across many different high level abstractions in different programming environments, including, for example, Java. Now, when we talk about a symbol table, what we're talking about is a particular data structure for key value pairs that supports two primary operations: inserting into the symbol table to put a new pair in, a key and its value, as well as to be able to search or to get the value assigned to a specific key. Okay, a simple example might be a DNS lookup table, where the table exists where you have on a DNS server a domain name and its associated IP address. We could give the key as the domain name and its value the IP address. And to insert into this table would mean to add one of those key value pairs, to be given a key, that is, to be provided with the URL or domain name. The lookup process would then try to find in this symbol table the corresponding IP address that goes with that key. And as you can imagine, there are a lot of different applications where that kind of key value pair would play a significant role. For example, here's a whole table straight out of the book: dictionaries, book index, file share, web search, compiler, routing table, reverse DNS lookup, which switches the role of the domain name and the IP address, even in applications and research and scientific applications like genomics. You can have where you would have a particular genetic marker that would be associated with a DNA strain or a string of the DNA sequence. Okay, so the key value pair would be the DNA string and then their known positions on a given genome. So I just want to point your attention to this basic symbol table API. And just for reference, I am only hitting really the highest points in this section, and would encourage you to make sure you read this section. Make sure you're also, if you have the time, to watch the videos provided by the author, Robert Sedgwick, because he does an even better explanation. But I wanted to point you to the things that I think are most important for you to make sure you know and are familiar with whenever you start working on the homework. And this basic symbol table API is important because this is how you're going to construct a symbol table that we will use both in this section and future sections, and these are the basic methods you're going to be calling. In particular, you're going to be looking at the ability to put a new key value pair into a symbol table. So the key and the value, depending on what type of application we're working on, can be just about any type of Java object that we're working with. I mean, if you wanted to think of key as an integer value and val as like a string, then you could just as well think of this as the way that you would set up a string array, right? Where you have a particular array A, and then you reference by using key, which is an integer, the value that goes with it. So a symbol table is a generalization of this array approach, and then to get a value out of the table that corresponds to a specific key, it's the same as whenever you reference A with the brackets around the key, which the key in this case is an integer, but now these pairs can be anything, like we saw in the applications or the examples that I gave you on the previous slide. Okay, so contains is a check whether or not that value is actually paired with a key in the table to be able to remove a key and its associated value from the table is another method. You'll have a couple here to check whether or not the one is the table empty, two, what is the size of the table, that is the number of key value pairs that are actually in the table, and you should be able to also iterate over the keys in that table. Now this ordered symbol table API is a broader API that includes, as you look through this, notice there are several more methods available to you, including min, max, floor, ceiling, rank, select, delete, min, delete, max, number of keys between a low and high, that's the size, and also iterates not only over keys but over a subset of the keys, a value from low to high in a sorted order. These functions or these methods aren't available in your general API, in that more general one we looked before, because we're again looking at a key value pair where the two values, the object for key and the object for value, are not necessarily comparable. So keys aren't necessarily even sortable in general. If you allow the keys to then be of a type that can be sorted, that can be compared, less than, greater than, then you are able to implement these particular methods. And Dr. Sedgwick, in his video and also in the text, you'll read through what each of these particular methods mean. But whenever we look at the two elementary implementations that are in this section, let me look up the names of these because I keep forgetting them. The linked list implementation that's unordered, and then the binary search implementation that is ordered. The first of those two, you wouldn't be able to do this. Actually, you are able to do this. Depends on what kind of key type that you use in the table. It doesn't depend necessarily on the implementation. Sorry, let me be clear. So in the two applications that he mentions in this section, there's one that's just assigning an index, a single integer value to whatever input is coming in standard in, and you just count up the number of which string is being entered into standard in and assign it to that. Well, that was the 0th one, that was the first one, that was the second one. That particular application you could also do these particular methods with, and also the frequency counter that he talks about in this section also has available to it these applications, these methods as well. I tell you what, as I was looking back through the text, I noticed that the book actually doesn't go through these two test clients, so I was referring to these two applications where you are able to implement some of those ordered symbol table methods. One of them he mentions in the video is called the symbol table test client for traces. In this particular client that utilizes a symbol table, you'll notice that the symbol table here is created where the key is going to be a string and the value is going to be an integer. And so what this does is this takes in a string, or sorry, a set of string values from standard in and assigns to it an integer of which value is that particular string. So when S is entered, it associates the value 0 with it. When E comes in through standard in, it associates with 1. A, the value is 2. The key R, the value is 3. C is 4, H is 5, E. Now E is interesting because with a symbol table, the keys, at least in the implementations that we're going to be utilizing in this course, the keys have to be unique. There are no duplicates. So whenever E is then entered into the symbol table, whenever it is put, it will replace the existing key value. That is the value that is associated with the key E from being 1, which was already in the table, to now being 6. And in fact, if you look at the final output of this particular client, you'll notice that E has a value of 12 because the most recent, that is the last entry for the key E, turned out to be 12. Now, the keys in this case are comparable because they could be sorted. That is, they can be compared to one another as less than or greater than. So you could use some of those other implementations. The second test client that he mentions in the video for this course is the symbol table test client, which he calls the frequency counter, which will read a sequence of strings from standard input and print out the one that occurs with the highest frequency. So the way that this uses a symbol table is that each word in this string becomes a key. So the keys are strings, and then the value associated with each of those keys is the number of times that particular string occurs. So in this case, it's going to be separated because they're going to be tokens coming through the stream of standard in. They're going to be words separated by spaces. So in this particular example, the way this frequency counter is set up is that the command line argument here is the size of the words, that anything less than that is not counted, and then this is a text file, for example, being strung in. It's a set of text from The Tale of Two Cities by Charles Dickens. It turns out to be the most frequent. It's just incrementing the key the value that is associated with each word that it finds. Okay, and you can see that that implementation is relatively simple. Again, you create a symbol table object where the key is a string, the value is an integer, and then as it reads these strings in through standard input, if the word length is less than that minimum length, then it's going to break out and not count that. But if then the symbol table does not already contain that word, it would put that word in there with a value of 1. Otherwise, it would update the word key with a value that is the previous value plus 1, so it increments it. And then this is what it outputs at the end, is the one with the max. So it would search through and find the one with the highest number of count that occurred most frequently. In one of the homework questions, I asked you to perform a trace of the linked list, the unordered linked list of key value pairs, that particular implementation of the symbol table. This is the example that I want you to follow in that particular problem. So either drafting by hand or writing it out in a word processor or something like that, this is what a trace of that would look like. Similarly, if you wanted to perform a trace of a binary search symbol table implementation, then you would do it similar to what we have right here, with the keys on the left and the values on the right. And notice then the way that the binary search insert process is implemented is that it searches for the value of the key, where you would then insert that particular value and then shift the rest of the keys and the values to the right and insert that particular value into the symbol table. There are two very important tables that I want you to make sure that you are familiar with and that you know well, and that's the implementation order of growth for the sequential search or the unordered list, and the binary search, which is the ordered array that we have in there. Plus, there's a second table that I want to show you in just a second that's also in the book, but I want you to be familiar with it as well. This one, says that we're guaranteed to have for a sequential search that unordered linked list implementation. It takes no more than n. Depending on the size of the array, that n is the size of the symbol table, to do a search, to look up or to get a value associated with a particular key, and to insert a new one is also n. But because on the unordered list you're searching through, on the average case with random key values, you're going to have an average case of n over 2. The insert case is still going to be n. For a binary search, you actually have an optimal search. That's as good as you need to get for the log n for the order of growth of either the guarantee or even the average case. However, the insert for the binary search is still n here, and the average case is n over 2. When you look at the table for the additional methods that are in the expanded API for a symbol table that include when you're using a comparable key, search, insert. Of course, those are from the existing table, but finding the min, the max, the floor, the stealing, the rank, select, and doing an ordered iteration, you see here what those particular order of growth for running time for those ordered symbol table operations would be.